Acid-base theories. This will be especially useful for students taking Chemistry 132 next semester because it is covered a little bit in the Introduction to Chemistry class, and we don't really cover this until second semester, Chemistry 152. There are several different definitions for acids and bases. The ones that we have been using have primarily been the Arrhenius definition. And the Arrhenius definition says that acids produce hydrogen ions in water and bases produce hydroxide ions in water. This really limits us to having reactions that occur in water, and we are really talking about classic acids and classic bases, the way we learned to look for formulas for acids and bases in our types of compounds. The Bronsted Lowry definition extends that a little further. It identifies an acid as being able to donate a proton, and if you think about hydrogen, hydrogen has one proton and one electron. If you make it a hydrogen ion, you just have that one proton. So a hydrogen ion is a proton. And bases as proton acceptors. This extends the definition to allow other solvents, and it also allows another whole variety of reactions to be classified as acids and bases. You'll see when we look at it later, you don't have to be a classic hydroxide or start with hydrogen to be classified an acid. There is an additional theory where the acids accept electron pairs and bases donate. You will see this used in organic chemistry, particularly being able to classify carbon as an acceptor or donator of electron pairs, and extending that definition even further. The Arrhenius definition, which we use the most in general chemistry, here's your classic acid, starting with hydrogen. And in solution, if this occurs in water, you produce hydrogen ions. And if you're a strong acid, this is a one-way reaction. If you start with 100 HCl's, you end up with 100 H's and 100 Cl's, and there will be no HCl's left. Acetic acid is a weak acid. It partially dissociates. Again, it's a classic acid. The way it's written, it starts with hydrogen. If you had 100 of these, approximately 5 would dissociate. So you'd have 5 of each of the ions, and then you would have 95 of these left in solution. And it's a dynamic equilibrium. Here's sodium hydroxide, which is our classic base, and it's a strong base, so it totally dissociates. For every 100 of these I put in solution, I have 100 of the ions and none of the sort of molecular species. Now, Bronsted Lowry is able to extend our definition of acids and bases. And when we look at two substances reacting, we're going to look at which way the hydrogen's moving. And I'm actually, I think, going to write these reactions 2 different ways. I'm going to designate which one of these is going to be the acid. And the acid is the one that is donating the hydrogen ion. The base is the one that's accepting it. Well, if this H2PO4- donates a hydrogen, it will only have 1 hydrogen left, and it's donating its positive charge along with the hydrogen, which means that the charge is going to go down 1. Water, on the other hand, is going to pick up that hydrogen, so it's going to have an extra hydrogen on it, but not just an extra hydrogen, but an extra positive charge. Now, this reaction is a 2-way reaction, so if I look at what happens on the way back, I know that that H3O is going to become water, so the H3O is going to be the acid, is going to be the donator, and the HPO4 minus 2 is going to be the base. So I've designated my acids and bases. Additionally, you will see that I can connect what we call conjugate acid-base pairs. And if you look at my conjugate acid-base pairs, I've got H3O plus as an acid and H2O as a base. And I also have H2PO4 minus as an acid and HPO4 minus 2 as a base. You should be able to see that the only difference between these is the number of hydrogens and the charge. And for the second reaction, I'm going to choose water as my acid, and water is going to lose a hydrogen and become OH, not HO, but OH minus, and then I will have NH4 plus. I'll just have an additional hydrogen on the NH3. And in reversing the reaction, this is my acid and this is my base. So my conjugate acid-base pairs now are H2O and OH minus, and NH4 plus, and NH3. This would be the acid and the conjugate base. So that extends things. For example, NH3 doesn't look like an acid or a base. It's not written to look like either one. But notice that when I put it in water, because it actually pulls the hydrogen off of water, it makes the solution basic. This is from page 59 in the back of your textbook. And you can look at taking an acid and turning it into a base, or vice versa. If we have an acid and we go to a base, we are going to lose a hydrogen because acids donate hydrogen, and we're also going to decrease the charge. On the other hand, if you go in the opposite direction, you will gain a hydrogen and you will gain a charge. For example, H2PO4 minus, if that's the acid, it will lose one of those hydrogens and it will lose a charge. And when you're talking about losing charges, you want to be on a number line. This is going up the number line, this is going down the number line. We could write an equation for what happens, and this is sort of a half reaction. We pull off the hydrogen ion and we're left with the conjugate base. So this is our conjugate acid and this is our conjugate base. Notice in this reaction the atoms balance, but there's a -1 charge on this side, and +1 minus 2 gives you a -1 charge on the other side. Let me take a look at this one right here. This is an organic acid. When it gains a hydrogen, you can put the hydrogen in the front or you can put the hydrogen in the back. But you don't want to write this, because if you see that CH4, you have a carbon with 4 hydrogens around it and it cannot be attached to anything else. So the acid hydrogen either goes in the front or in the back with the COOHs. So that's an example of using Bronsted Lowry acid-base theory And notice that the only thing you are changing is the hydrogens. Don't change the number of oxygens. The only thing you do is put a hydrogen in front of it, or you take a hydrogen away from it. And note that the conjugate base of water is OH minus. By the way, water is one of several substances that can be what we call amphiprotic. If this is an acid and this is its conjugate base, this is an acid and that's the conjugate base. Water can be either an acid or a base, and that is called being amphiprotic. So that's just a fancy word. But several other things can do that. For example, H3PO4, H2PO4 minus, HPO4 minus 2, and PO4 minus 3. The two in the middle have the ability to be either an acid or a base, where this one will be a base only and this one will be an acid only. So that's a review of Bronsted Lowry acids and bases.